Okay, welcome everyone. So yeah, today we're happy to have Asilata Bapat from ANU, and she's going to talk about a Thurston compactification of Bridgeland stability space.
Okay, thank you so much, everybody, for coming. Arik, for the invitation. It's really nice to come back in some sense. So my talk today is on a Thurston compactification of Bridgeland stability space. Hopefully, I'll get to explain all these words, and we'll see how to go from there. So let's just see if I can. There it is. So it's joint work with Anand Deopurkar and Anthony Licata, who are both here at the ANU. And we have a recent preprint on the archive as of a couple of weeks ago. So you can check that out if you're interested. So let me just start with the general setup and general motivation. I haven't given too many talks over Zoom, so if you have any questions, please feel free to interrupt. I'm happy to answer them. I don't have a specific agenda that I have to cover, so yeah, happy to have a discussion. So the setup for this whole story is that I'm going to be starting with the triangulated category. Now, I appreciate that not everybody works with triangulated categories. So an example to keep in mind would be if you have your favorite algebra, you could look at the bounded derived category of your favorite algebra. So that's a good prototype example to keep in mind. Other people look at the bounded derived categories of coherent sheaves on an algebraic variety. That's another nice example to keep in mind. If you are also not happy with those examples, maybe you can just decide to take it on faith that a triangulated category is a category with certain extra nice features, which will be useful for us. So the features that we are interested in are the following. I mean, these are sort of the basic things that we want from a triangulated category that they satisfy. So every triangulated category has what's called a shift functor. So it's an automorphism, if you like, of the category. So if you have a bounded derived category of something, so it's a category of complexes, typically the shift functor shifts your complex left and right. So you have the shift functor 1, but you also have the shift functor -1, -2, +1, +2, etc. And you have the notion of distinguished triangles, which look like so. So A, B, C to A shifted by 1. And so we should think of triangulated categories as more flexible versions of abelian categories. We can do a lot more with them. And distinguished triangles, people always say they're replacements for short exact sequences. So if you're happy with that, I'll move on from there. So this is our basic setup. And often when we look at triangulated categories, we have bounded T structures on triangulated categories. So again, for example, if you have DB rep A, let's say your favorite algebra, the category of representations of your algebra sits inside the bounded derived category of representations of your algebra. And what we have is that, can you see my point? Yeah, there it is. So, a bounded T structure cuts up our category into pieces indexed by integers. So the 0 level piece is an abelian subcategory, which is typically called the heart. And so for us, it would be rep A. And you can take rep A and you can shift it around by the shift functor. And that gives you shifts of the same abelian subcategory. And we should, in some sense, all of these shifts fill out the entire category. So what does that mean? It's not the case that every object in your category lives in exactly one of these shifts, but every object can be broken up into pieces which live in exactly one of these shifts. So if you kind of take the cohomology filtration of any object in your category, each subquotient, if you like, a filtered piece lives in one of these shifts. So this is what a bounded T structure looks like. And often we have bounded T structures. For example, DB rep A comes with its own standard T structure. You could also have non-standard T structures, and it's useful to vary your T structure around. You can get more information about your category by breaking it up into pieces of a different shape. And so especially if you have more than one T structure on a category, you can get quite nice pieces of information. For example, you may have heard of the perverse T structure on a category, but there are other examples, of course. So it's useful to vary our T structures around. But the problem with this is that they don't vary continuously or nicely. And so varying a T structure is useful, but there isn't a nice parameter space of T structures, unfortunately. So the very nice and deep replacement of that is the theory of Bridgeland stability conditions. So the approach that we have is, the approach that we should think about is that a Bridgeland stability condition is a T structure together with some other information which lets you vary the T structure around. So again, if there are any questions, please feel free to stop me at any point. It's hard to gauge in a Zoom audience. So let me say a little bit about what a Bridgeland stability condition is. So in this entire talk, I won't be extremely precise about anything, but again, I'm happy to answer questions, and I would like to give the flavor of what we're doing here. So yeah, so what is a Bridgeland stability condition? So I like these horizontal diagrams that some people use quite a lot in their papers. So so let me go back to our diagram about T structures. So this diagram for a bounded T structure is cutting up your category into pieces indexed by integers. Now, we should think of a stability condition as an R refinement of a T structure. So we still have the same category C. It's a triangulated category, which we think of as kind of a real strip. But this time, instead of cutting it up into integer pieces, so I still have these little blocks, these blue blocks, sorry, which were my original integer pieces. I don't know if the colors are visible at all. But now, in addition, I have a further refinement of my category, and I have pieces of my category that are indexed by real numbers. So previously, this entire collection, so starting at this blue line here, ending at this blue line here, was, let's say, the heart of my T structure. And now the heart of my T structure has been further broken up into additive subcategories indexed by the real. So in this case, the heart of my T structure I should think of as not the piece living at the integer 0, but rather the piece living at the interval from 0 to 1. Okay, and then within that interval from 0 to 1, I have a further subdivision, and I might have subcategories indexed by numbers in between. For example, I might have a subcategory indexed by the number 1/2. And some of these might be empty, but this is why I've sort of drawn this as a kind of spectrum. So at several values of phi, you will have some subcategories sitting in there, and then this whole structure is periodic. So this is the picture that I want to emphasize more than the definition. And now the idea is that we previously, our T structure, you could only sort of shift left and right by multiples of 1. But now that we have an R refinement of this T structure, you can shift the whole thing left and right, not necessarily by multiples of 1, but also by any real number that you like. So that's the beauty of introducing this new notion. Are there any questions or comments so far? Okay, so maybe I'll move on and give some sort of definition. Oh, before that, maybe I should say something about why we like them. So I already mentioned one thing. So the collection of all the stability conditions on C forms a nice parameter space. In fact, Bridgeland's theorem is that it forms a complex manifold, which is extremely nice. Given any triangulated category, there is a canonically associated complex manifold, which is the collection of all the stability conditions on it. Now, in general, these are not so easy to compute. And often, when Bridgeland started the story about 20 years ago, a lot of the work was done in sort of more algebro-geometric settings. So for derived categories of coherent sheaves on a certain variety. And we will focus a little bit more on more algebraic examples. And in those cases, computations will be a bit easier, but also there will be a lot of other non-trivial structure. And the second point that I want to make is that this space stab C, which will be my notation for the stability space, carries an action of the autoequivalence group of the category. So every triangulated category, or any category really, you can think of autoequivalences on the category. So equivalence is from the category to itself, and of course that forms a group. It's the symmetry group of the category. And since stability conditions or stability space is a completely natural construction, the same group also acts on the stability manifold or the stability space. And this is an action that we will be interested in our setting. And I want to make the point that studying stability space in this setting can give you more information about this autoequivalence group. So we'll come back to this in a moment. But these are the properties that I'm looking for, or some sort of motivation. So let me give a somewhat vague definition of what a stability condition is, or rather, this is more like a recipe that specifies how to construct one if you have a triangulated category of your choice. So often, as I said, your triangulated category has a T structure already, so you may as well use that. So the starting point is the heart of a bounded T structure on your category. And the extra piece of information that we need to impose on this heart to construct a stability condition is something called a central charge function. So this is a Z, and what is it? So we have our abelian category, which I've called the heart. Now, associated to that is the Grothendieck group of the category. So I should have probably written those words, but anyway, K of heart is the Grothendieck group of the abelian category, which is the heart of the bounded T structure that you start with. Now, so the generating objects are just the objects of your heart, and then you have relations given by short exact sequences in your category. Now, what we need, the extra piece of structure we need, is a group homomorphism from this Grothendieck group to the additive group of the complex numbers. So every object in your category, so to produce a stability condition on your category, what you have to do is you have to take every object in the heart and you have to associate to it a complex number such that this association gives you a group homomorphism. And furthermore, you need the objects of the abelian category that you start with to land in the upper half plane. Now, this is all a bit, I mean, this is quite a lot to take in. So I will give you one example of how to actually construct a stability condition in our setting, which hopefully will make things more clear. But basically, it's the heart plus an extra complex number for each object. And all of this has to satisfy some compatibility conditions, which I will maybe hint at in a moment. Okay, so starting with the T structure plus some extra information gives you a stability condition. It's not always easy to construct them, but in many of the examples that we do have constructions. So let's see if I can show you. Oh, and then there is something about stability. So every object in the heart is either semi-stable or it's not, and there's a certain condition. So I'll read this out, but I'll go back and do the example first so that we can see what's going on. So we say that an object X is semi-stable if whenever you have a sub-object, the angle corresponding to the sub-object is less than or equal to the angle corresponding to the original object X. So remember that every object has an associated complex number, so you can plot it on the complex plane, and then it has an argument. So once you have specified a group homomorphism Z, all you have to do is to check which objects are semi-stable according to this definition. So as I said, I know that this is a lot to take in if you haven't seen it before, but let me try to do an example, and maybe I'll come back to this slide just to see if it makes sense. So I just want to do a really baby example just to see that we can actually construct these things getting our hands dirty. So my category is going to be the bounded derived category of representations of the A2 quiver, which I've drawn here. Now, hopefully this is somewhat familiar. This has two simple, this category, so the representation category of this, this A2 quiver has two simple objects, S1 and S2, which I've drawn this way. It doesn't really matter what they are for the moment. And then it has another indecomposable object, which is an extension of S1 and S2. And the short exact sequence that defines this extension is here. So we have S2 is a sub-object of this object E, and S1 is a quotient. And mainly, this is what this is the main thing that we should remember. So what I'm going to do is I'm going to construct some stability conditions on this category, just to show you how one actually might do this. So remember that there are three indecomposable objects here, S2, E, and S1. And I'm focusing, of course, on the standard heart, which is just the representations of A2. Now, I'm supposed to give a homomorphism from the Grothendieck group to C. I have two simple objects, and they generate the category. So as long as I can associate a complex number with each S1 and with S2, the number associated to E is completely determined, because in the Grothendieck group, E is the sum of S1 and S2. Mm-hmm. So all I have to do is write down a complex number for S1 and a complex number for S2, and then E will be the sum of those two complex numbers, and then I have to check which objects are semi-stable. So there are two basic cases here. The first case is that I put S1 sort of to the right of S2. So remember that my objects in the heart have to lie in the upper half plane. So this is my upper half plane, let's say. And so S1, the first basic case is that S1 has smaller angle than S2. And the second basic case is that S1 has larger angle than S2. And of course, there's an intermediate case that I haven't drawn, which is that S1 and S2 coincide in angle. But let's forget about that for a second. These are the two sort of non-degenerate cases in some sense. So S1 has smaller angle than S2, S2 has smaller angle than S1. So now let's look at this object E. The class of this object in the Grothendieck group has to lie on the ray that is the sum of S1 and S2. That's by construction, because E is the sum of S1 and S2 in the Grothendieck group. But whether or not E is semi-stable depends on the relative positions of S1 and S2. So let me go back to the previous slide. We say that an object is semi-stable if whenever you have a sub-object, it has smaller angle than the original object. And so here we just go ahead and test that condition. E has one sub-object, namely S2, and we see whether or not S2 has smaller angle than E. And in this case, E has smaller angle than S2, so E is not semi-stable. In this other case, E has bigger angle than S2, and so E is semi-stable. So this is these are two kind of distinct possibilities for stability conditions on this category. Are there any questions or comments about that?
Yeah, I have a question. So
yeah,
looking at the path algebra of like a quiver, a Dinkin quiver. So you have finitely many indecomposable modules, and I think they're given by the number of positive roots. Is that correct? Mm-hmm. So in general, can you can you do this for any sort of root system?
Yeah, you could. In general, for any, if you have finitely many simples, it's in some ways very easy to write down a stability condition of this type. You just put the simple somewhere on the plane, and then the other indecomposables will live at certain positions on the plane based on their decompositions, and then you just check whether or not they're semi-stable. So for these categories, it's actually in some ways quite easy to write down a stability condition. There isn't any other compatibility. The compatibility follows.
Okay.
So this is the easiest example. Yep.
So in this case, can you write down the stability space? Is it nice? Can you describe this?
In this case, basically these are the only stability conditions that you can write down. Yeah. So yes, you can write down the stability space. I have to think about what it actually is, but basically these are the only two things you can do, and then you compute the parameter space. So basically, what you do is you have one vector for S1, one vector for S2. They can be anywhere on the upper half plane, and then you have to think about other T structures. So I think it's probably like C2 or something like that, something easy. That you can write down.
Mm-hmm.
Yeah. let's see. Is there any other comment that I wanted to make here? So, sorry. So the comment that I want to make is that I have only written down stability conditions on the standard heart of dB rep A2 or dB of whatever category that I want. In principle, you could have chosen a different T structure with a different heart and done a similar thing for that new T structure. And so to compute the entire stability space, you have to do this for every possible T structure in principle. But in this case, it actually isn't that bad. Right. So the merit of stability conditions, I already mentioned this, is that unlike T structures, stability conditions can be deformed continuously if you deform this function Z or Z. Sorry, I'm in Australia now, I say Z. So if you go back here, for example, let's look at this, this first kind of stability condition. So I have, my chosen complex number for S1 and my chosen complex number for S2, I could sort of deform them a little bit, and the shape of the stability condition wouldn't change. The shape of the stability condition only changes if I cross over S1 and S2, and that's called a wall crossing. But in general, what you could do is you could deform S2, for example, you could rotate it a little bit to the left, and that technically gives you a different stability condition, even though it has the same sort of shape. So since the Z is different, you get a different output. So you can, of course, think about rotating S2 now to the left and continuing to rotate S2 sort of past the real axis. And that would sort of change the T structure. So this is, one has to think about this a little bit, but the point is that if you deform your stability condition by deforming Z, the T structure that you had will change as you do this. So you may have started with some original T structure, which I've called the heart, or the heart of a T structure. And as you deform Z, this heart will change. So if you deform a little bit, it won't change probably, but then if you continue to vary Z, you will get different hearts and therefore different T structures in the process. So this is a way of kind of interpolating between several T structures. And again, I already mentioned that the space of stability conditions is a complex manifold. We typically mod out by a natural action of C. So the action of C is just basically on Z. So I don't want to say too much about it, but the stability space is a complex manifold. And a key property of these stability conditions is what's called Harder-Narasimhan filtration. So I'll explain that in a moment. So sorry, I wrote theorem. This isn't really a theorem. It's I don't know what to call it. It's not a theorem, but a construction, maybe due to Bridgeland. So if tau is a stability condition, then every object of the heart has a unique filtration such of this nature. So basically, one merit of stability conditions is that even if you have non-semi-stable objects of the heart, so it's much easier to understand sort of semi-stable objects of the heart. But if you have other objects of the heart that are not semi-stable, you can nevertheless decompose them uniquely into semi-stable objects. So every object has a unique filtration such that each subquotient is semi-stable and the arguments are decreasing. So again, the details at the moment, they're not so important, but the point is that a stability condition gives you a way to decompose every object of the category into a successive extension of semi-stable objects. And this should be thought of as similar again to what a T structure gives you. So if you have a T structure, any object of your category can be broken up into pieces, each of which live inside a shift of the heart of the T structure. So this is, again, a refinement of the notion of a T structure. So this, I wanted to mention that because it's important, but actually it may not come up again in this talk. Okay, so let me now move to the main example for this talk and the main example that we will work over. So our category C will be KB proj of what's called a zigzag algebra. So again, I don't want to give the definition at the moment. I'll give you a specific example in a second. Yeah, sorry? Yeah, I'll give you a specific example in a second, but let's just say it's some finite dimensional quotient of some path algebra of a double quiver, and typically Dinkin quivers, much easier to do AN quivers. In fact, in this talk, I will only do the A2 case. So it's we will focus on, for this talk, the zigzag algebra of the A2 quiver. And then I'll look at the bounded homotopy category of projective modules of this algebra. So let's not worry so much about what exactly the category is. I'll give you the important pieces in a minute. So the zigzag algebra is nice. Lots of people study it. And as many of you know, the Argentines braid group of the quiver shows up in this setting. So if you have, for example, the type AN quiver, you will have a braid group, a standard Artin braid group, which will act on your category. And this braid group acts by autoequivalences on the category and therefore also acts on the stability manifold. So as I explained earlier, we are interested in the stability manifold, one reason being that the autoequivalence group of the category acts on this space, and we'd like to understand something about it using this action. So this is what we'll be interested in. But again, the main example will be type A2. So we will be looking at the 3-strand braid group action on a certain stability space. Yeah, as I said, so the zigzag algebra for type A2, and this is the picture. So of course, again, you have an A2 quiver, but of course now it's a doubled quiver this time. And the path algebra is generated by A and B together with these idempotents. The relation that we impose is that any length 3 path is 0. So ABA equals BAB equals 0. And so it's a finite dimensional algebra, and it has 2 generating modules. So we are only interested in projective modules over this algebra, and projective modules are typically given by idempotents. So if you have an idempotent, you can produce a projective module by looking at your algebra and hitting it with the idempotent. So we have 2 vertices, and so we have 2 basic idempotents. The one at this vertex here, which we call E1. So the module somehow at this vertex will be P1, and here you have P2. So this is similar to the simple modules S1 and S2 that we had previously for our just the dB rep of A2, but this time they're, sorry, they were simple modules, but anyway, we are interested in the projectives. So the main feature of our category will be that it will be generated by these 2 basic projectives, and moreover, there is going to be an action of the 3-strand braid group on this category. So you will have images of P1 and P2 under the action of the braid group, and they'll give you lots of other objects of the category, and basically we want to leverage this and study the stability space. Any questions here?
So modules over this algebra is really just some parabolic category O, right?
Yes, I think so. I think so, yeah.
Okay. Mm-hmm.
Unless there are 2 versions of the zigzag algebra. Now I'm a little unsure which one you mean, but yeah, I'll have to think about it. But I think some version of this does give you a parabolic category O.
Mm-hmm.
Yep. Yeah, so great question, because obviously, as you can see, there are obvious generalizations to this, of this story to other bigger algebras. At the moment, we are looking at these small ones. Okay. So as I said, C, our category, let's not worry about exactly what it is, but it's generated by 2 objects, P1 and P2. And the main feature that I want to highlight for these objects is that these objects are what are called spherical. So the endomorphism algebras of each of these objects look like the cohomology ring of a sphere. So in particular, if you look at the degree K maps from, let's say, over coefficients in C, but degree K maps from P1 to P1, then you get a copy of C in degree 0 and a copy of C in degree 2, but you get 0 otherwise. And the multiplication structure is also what you want it to be. So somehow these objects yeah, the self-harms behave like the cohomologies of a sphere. And a general fact is that if you have spherical objects in your category, we have associated autoequivalences. So every spherical object gives you an equivalence from the category to itself, and these are called spherical twist autoequivalences. So I could give you a precise definition, but I don't think it's necessarily helpful at the moment. So I'll just leave it at this. So somehow each, so associated to P1 is an autoequivalence from C to C, associated to P2 is an autoequivalence from C to C. And the great thing about this is that these two generating autoequivalences, well, not generating, these two autoequivalences satisfy the braid relation. So I mentioned that the three-strand braid group acts on this category, and this is exactly how it acts. So each P1 gives you a sigma P1, P2 gives you a sigma P2, and the standard braid relation that we know and love, sigma P1, sigma P2, sigma P1, is isomorphic to sigma P2, sigma P1, sigma P2. So that's satisfied by these two functors.
Quick question. Does
Yes.
this work just for any triangulated category, or do you need a Serre functor? Do you need a little more? Or?
Yeah, this is for a two Calabi-Yau category, but I think
you sort of started with by saying that you work with pretty arbitrary triangulated.
Sorry, no, that was just for the purposes of definition of the stability space and stability condition. So now we are really focusing.
At this point, you need a Serre functor.
Yes. So yeah, the other important feature of this category that I did not mention is that there is a Serre functor, and that this category is a two Calabi-Yau category, and that's somehow hidden in this definition of spherical twist autoequivalences. Yeah, so now we are specifying to these categories. Great, so now we have an action of the three-strand braid group, in this case, on our category. Now, as Valerie said, you could make this a bit more general. You could do this for zigzag algebras of arbitrary, let's say, connected quivers. In that case, you would have similar constructions, and you would get an action of the associated braid group on your category. So the braid group associated to type A2 is B3, but for an arbitrary, let's say, connected quiver, you have an associated Argentines braid group, and that will act on your category. So that's that is the underlying more general setting, but we will focus on A2 for the sake of clarity. And also because that's where we have the cleanest results.
I mean, these double Dynkin quivers are so special, right? I mean, it's many things are not true for other graphs. If you know,
yeah, that's right.
The ADE double graphs that you have these wonderful properties, such as this, Crepant resolutions, kind of maybe Calabi-Yau property. So
the Calabi-Yau property,
how much you can move to other graphs.
So the Calabi-Yau property will be satisfied for other doubled quivers as well. I don't think there's a geometric interpretation for an arbitrary quiver. If you take an arbitrary quiver, double it, compute the zigzag algebra, I don't know of a geometric interpretation, but nevertheless, algebraically, you can still do this almost, the same constructions go through. Again, you have a braid group action on the category, and that's one of the merits of this method. You create, in the absence of geometric examples, you can still study stability conditions on these kinds of quivers. So the main question, and at the moment this question might feel a bit unmotivated, but I'll say it anyway. You have this stability manifold, stability space corresponding to your category. And again, as I said, we've specialized now to the case of zigzag algebras corresponding to connected quivers. So is there a compactification of stab C such that the action of the corresponding braid group extends continuously to the boundary? So this is a question that we're interested in. As I said, it might seem a little bit unmotivated, but let me try to say some words about some sort of motivation for this. the first motivation is intrinsic. So if you go back to the definition of stability conditions, of course, I didn't give you the full definition, but there is an embedded sort of non-degeneracy condition for that a stability condition has to satisfy. So every stability condition has some sort of non-degeneracy property that it must satisfy. And what you might imagine is you might imagine taking a stability condition, you know that you're allowed to deform it. So you might try to deform and degenerate a stability condition, and you might hit a place that's not a valid stability condition. So somehow trying to deform and degenerate stability conditions naturally leads you to the question of trying to compactify it. So that's, of course, an intrinsic motivation.
Okay,
But-
can I ask? Can I interrupt? So,
Yes, of course.
So I'm just trying to remember. So if you start with a smooth projective surface, say a K3 surface, and you look at this Bridgeland space of stability conditions, is it already compact? It's a complex
I don't think
manifold,
so.
but isn't it?
No, it's not. It's not
some
typically
other-
non-compact. I don't think.
But sometimes isn't it sometimes just like another?
The reason is that basically, well, one of the hidden requirements in a stability condition is that, okay, one way to say it would be that indecomposable objects have a non-zero central charge. And if you just give an arbitrary central charge without any sort of, without thinking about it, then you might end up sending some objects to zero, and that's not allowed. So that's the sort of place where non-compactness shows up. And in later on, we'll actually construct stab C for the A2 case. So hopefully it'll be slightly more clear with the picture. Any other comments? I hope that answered the question. Right, and then the other motivation for trying to construct a compactification like this is that this action of B is quite interesting, and the expectation is that if you have a nice compactification such that the action of B extends to the boundary, then it should give you more information about B by looking at the action on the boundary. And I should have written something more here, but the title of my talk had the word Thurston in it. And the title was A Thurston Compactification of Stab C. So what does Thurston have to do with it? So the motivation really comes from Thurston's work on type Mueller spaces. And Thurston, so if you are unfamiliar with these words, that's fine. I'm not an expert on them either, but I would just like to quickly say what the motivation is from Thurston's work on type Mueller theory. So if you have type Mueller space associated to a Riemann surface, then Thurston constructed a compactification of type Mueller space such that the mapping class group of your Riemann surface acts also on the boundary of the compactification. And this compactification and this extension gives sort of a classification of elements of the mapping class group. So again, that was sort of just motivation, but on the other hand, there are parallels to this story. And what we would like in our setting is to find a compactification, extend the action of this braid group to the boundary, and see what structure you get on the boundary. So that's the main question that we're interested in. So let me see if I can say a little bit about it. So yeah, so the strategy that we will try to use for this compactification is it looks horrible. You embed the stability space into an infinite projective space, and then you take the closure. And the expectation is that at the end of this process, you will end up with a compact real manifold with boundary. So originally you had a complex manifold, non-compact typically. So hopefully at the end of this this journey, we'll end up with a real manifold with boundary. So the boundary of this should also be a real manifold. So more precisely, I would like to explain this recipe a little bit and then see if we can do some sort of example and and see what happens there. So what I would like to do is embed my space into, as I said, an infinite projective space. And what this space is it's P to the S. So remember that we had a collection of spherical objects of our category. So somehow spherical objects of the category play a very important role in the story. P to the S, what does this mean? This means you should think of this space as being functionals on the set of spherical objects of our category, but scaled by a simultaneous scalar. So this is like taking R to the S, subtracting 0, and then scaling by the reals, if that makes sense. So what this embedding is, oh, sorry?
A stupid question. It's a projective space over which field?
Over R, over R. Yeah. So these are real functions, real functionals on S up to a simultaneous scalar. So an element of this hugely infinite space should be thought of as a functional on spherical objects. So it takes in a spherical object and outputs a real number, and then everything is simultaneously scaled. So that's the projectivization. So how do we define this map? What we do is we take a stability condition here. So tau is usually my notation for a stability condition. And we send it to the following functional up to scaling. So this is, this will, let's see if this makes sense. So to each stability condition should be associated a functional up to a simultaneous scalar. And what is that functional? If X is a spherical object, what I'm going to do is I'm going to take the quote unquote tau mass of X. So I haven't explained this yet, but it's some way of measuring the size of X according to tau. So this is my definition of a map from stab C into P of S.
Is there a typo? You said S, but it's written X. You said you send in.
Capital, sorry, S is the, I've written this badly, but S is the set of spherical objects of C, yes, and X is a specific scale.
X is one of them. Okay.
Yeah. Right. So for every object, I have to give you a number, and the number is the tau mass of X, whatever that is. So more precisely, what is this? The tau mass of X, remember that each object of our category had a canonical Harder-Narasimhan filtration. So the tau mass of X is supposed to be the sum of the lengths of these functions Z applied to AI, where AI are the semi-stable Harder-Narasimhan factors of X. So this is a bit of a mouthful. So what I just want to say that basically every object X can be broken up as an iterated extension of semi-stables in a canonical way. And the size of any object, the mass of any object, is supposed to be sort of the sum of the sizes of the pieces that make it up. So it's sort of like saying, well, if you have any object in an abelian category, you can maybe break it up into its Jordan-Holder series and count the Jordan-Holder factors. So that's the flavor of what we're doing here. So instead of counting the number of Jordan-Holder factors, we instead take a finer invariant. We take the sum of the lengths of the central charges of sort of these Harder-Narasimhan factors of our object. So this is supposed to measure the size of our object in some way. And so this is analogous to a construction of Thurston that he did for Teichmüller space. So by the way, how much time do I have, Arik? I can...
10 more minutes, approximately.
Okay. Let's see. Probably, we'll see how long it takes. But the strategy for the compactification is to embed stab C into this huge projective space using this map. It's not clear why what I've written is an embedding in any way. It's not clear why it behaves well topologically, but that's basically what we are trying to prove. So this is the strategy. Again, as I said, it's analogous to a certain construction of Thurston. And now again, we are interested, as I said, in the boundary points. So so one way to approach the boundary is as follows. So you can take a particular element of your stability space and take a particular spherical object. So as I said, to every spherical object is an associated spherical twist. So that is an autoequivalence of your category. And this spherical twist, autoequivalence, acts on your category, it acts on your space of stability conditions. So you can, of course, take sigma x and act by sigma x on tau. And remember that we're embedding stab C into this big projective space using what's called the mass map, m tau. So one theorem that we prove in our paper is the following. So what we can do is we can take tau and we can start applying to tau larger and larger powers of this certain spherical twist. And as we do this, of course, this is an infinite sequence, so it may or may not limit to some place. And hopefully, we're looking for a compactification, so it should hopefully limit somewhere. So if you take the limit of this thing, you're taking a single stability condition, you're acting on it by spherical twists, powers of the same spherical twist. You take the limit. The limit is still going to be a projective linear functional on the set of sphericals. So this limit, whatever it is, it's some sort of functional which eats a spherical object and outputs a number. So the theorem that we prove, proposition that we prove, is that this limiting functional, what does it do on an object y? It gives you the dimension of the Helm space from x to y. So remember that we started off with a stability condition, which was quite an involved object, and computed from spherical twist and taking limit a certain functional, which is in some ways a quite natural thing to study. So just the dimension of the Helm space between two objects of your category. So you start with stability conditions. As limits of stability conditions, you discover Helm spaces between objects. So this is a nice reason to expect a nice boundary of your compactification. So in particular, the boundary of our compactification includes these sort of Helm functionals. So that's an interesting thing. So let me say something about the type A2 case. So Arik asked earlier, what can we write down the stability manifold? Well, in the type A2 zigzag case, you can write down the stability manifold. In fact, Bridgeland, Chu, and Sutherland have given a proof that the stability manifold is homeomorphic to an open unit disk. So if you like, you can think of this as a kind of hyperbolic unit disk, and the three-strand braid group acts on the stability manifold. On the right-hand side, the three-strand braid group has a map into PSL2Z, which acts on hyperbolic space. So that's the isomorphism that we have. So stability space as a complex manifold looks like hyperbolic space, hyperbolic plane, the hyperbolic plane, and the action of B3 is realized via the standard action of the modular group on the hyperbolic plane. So this is a theorem that they have. But the point is that stab C looks like an open disk. And what we are trying to do, of course, is trying to find a compactification. So we're trying to fill in the boundary of this open disk. So what do we think the boundary of this open disk should be? Of course, we really want the boundary of this open disk to be a closed disk. And in fact, this is the theorem that we're moving towards. So let me say a little bit more about this open disk here. So this open disk, I've drawn it as a sort of Poincaré hyperbolic disk model of, or open disk model of hyperbolic space. And this has a standard triangulation. If you don't know what that is, that's okay. Basically, I've cut up this open disk into these sort of hyperbolic triangles. And one of these triangles, remember that this is supposed to be representing points of the stability manifold. So one of these triangles corresponds to stability conditions of sort of this form, where P1 has lower angle than P2. So all stability conditions where P1 and P2 are semi-stable and P1 has lower angle than P2, all of them fill out this triangle here. So that's what one of these triangles is, and other triangles give you other types of stability conditions. And one of the theorems that we prove, rather it follows from the previous proposition, that if you try to approach the boundary, you get, so within this triangle, let's say, you get 3 boundary points. And these 3 boundary points correspond to sort of the 3 semi-stable objects in the heart. So in this case, the heart has 3 semi-stable objects, P1, P2, and this third object, P2 to P1, which should be thought of as an analog of that E. And as you approach the boundary, when I say that you get P1 here, this is the Hom functional corresponding to P1, and this is the Hom functional corresponding to P2, and this is the Hom functional corresponding to the other object. So moving from stability space and approaching the boundary, you reach these are the sort of Hom functionals that I mentioned before. And so more precisely, the theorem is as follows. If you do this in type A2, so this is just a theorem for type A2 at the moment. So our recipe takes stab C, which was an open disk, and the compactification ends up being a closed disk. So it's an easy but pleasing picture. And the spherical objects in this whole story are indexed by Q union infinity, and they're dense in the boundary. So it's not true that every boundary point here looks like a spherical object, but these kind of fill out a dense portion of the boundary. So that's the description that we have in type E2. And I'll mention a couple of things. We also have a similar theorem for type A1 hat, which is affine A1 type. And I just want to leave you with this picture here. I mean, this is the previously you had an open disk closing up to a closed disk, and sort of the basic tiling object here was one triangle. Here we have a similar object, similar picture. The closure of stab C under the mass map is compact in A1 hat, and the spherical objects form a dense subset of the boundary, and sort of the tile, if you like, is this kind of infinite polygon. So you might imagine in other types, you might have similar things. So I had a few more slides, but I think in the interest of time, I'll skip some of them. Maybe I'll just go through. So right, so I guess we have a proof strategy. Of course, we need that. So we have to show that this map is injective, that its image is compact, that it's a homeomorphism onto its image, and then we have to compute the boundary. So the first two of these we can show for any connected quiver. Showing that it's a homeomorphism onto its image is the key hard step. And we do this using a new object, which we call Harder-Narasimhan automata. So unfortunately, I don't have time to go through them, but they're a fun little thing, but I'll just show you a picture. So Harder-Narasimhan automata are certain new gadgets that we introduce, which sort of looks like this, and they let you compute the group action on the boundary. And so that's what we basically use to show that the map that we have is a homeomorphism onto its image, and then we can find its boundary points. So yeah, future directions, you can try to do this for other types and try to deduce other results about the actions of the corresponding break groups. Yeah, so that's all I had. Thank you very much.
Okay, thank you very much. Yeah, please let me know if you have any questions, or yeah, are there any questions?
Well, I have a question.
Yes.
So I just looked up this old paper of Bridgeland, one of the first on the subject, where he computed the space, Bridgeland space, for a K3 surface. And the answer is that it's a positive cone minus hyperplanes to minus 2 curves. And of course, the question is, well, so what happens? Like, what do you expect as your compactification in this case?
For the K3 surface?
Yeah.
That's an excellent question. I don't know what the answer should be.
Yeah, as I said, the space is known. It's it's easy.
Yeah, I agree. I agree that is that's something that we should definitely think about, and we are thinking about in some way. But of course, these algebraic categories are much easier in many ways to tackle than the categories of K3 surfaces. On the other hand, categories of K3 surfaces also have nice spherical objects, so one can hope to run the same recipe. Indeed, the recipe should go through just as it is. Whether or not which properties of it hold and what the answer is, I don't know off the top of my head, but it's definitely something we're thinking about.
Another question, if I may. So this picture with the Poincare disk, right, and PSL2 acting on it. Of course, if you divide the open disk by PSL2, you just get A1, right? You just get complex, you just get C. And then there is a compactification, which is P1, adding 1 point. And that corresponds to adding the rational points on the boundary, which seems to be exactly as adding your spherical objects. So it seems that, this, very classical picture is, it's not a compactification of the space, but it's compactification of the space maybe by B, by braids or by PSL2 in this case. It's just, I was surprised once I saw the Poincare disk, I sort of expected a modular curve compactification. So then you look at the rational closure of this disk, right? And
yes, but to compute, yeah, that's right. But then you also fill in the real points as well. So the real points don't have an interpretation as objects.
I understand that you do, but I'm saying alternatively, you can compactify not this space but the quotient. And then you don't need to add all the points on the boundary, but only
that's true. Yeah.
the rational. So.
Right.
And maybe right. there is such a picture for in other cases. That's what I'm saying.
Yeah, that's
where you
right. Maybe
don't compactify the space. You want to compactify the quotient by
by B. Yeah. I guess that's true. Yeah. Although somehow one thing we do want to see is the action of B on the boundary. So I'm not sure. This sort of kills it already.
Well, it acts because you're compactifying the quotient.
Oh, because that's right. I see. So you're saying that if you take the quotient and you look at the compactification, you don't have to worry about these funny real points at all. You just
in this case, if you just add the rational points, then the quotient is already compact.
Yeah, I agree. I see. Yeah.
It's not the Teichmüller space. It's sort of the modular curve. But maybe there is, I don't know, maybe there is such a picture in other cases, maybe in general.
There should be, we expect that there should be something like this, although calculations have been limited so far.
Okay, any more questions?
I'll ask one more.
Okay.
Is there a stupid 1-point compactification? Can you do that? Just add 1 point at infinity. What do we call it? The Uhlenbeck compactification or something like that. But yours is nicer. So
Okay. More questions. Okay, this does not seem to be the case. So yeah, let's thank Asilata again.
Thank you all.
Thanks.